we still wait some minutes, about 3 minutes, for example, for.
Yeah, no problem. Okay, I will then reshare later on, maybe. I think. Yeah. Yeah, so for me, it's so different that all the names are showing up in Russian. I cannot even guess the first word, I think. Yeah.
Special for you, I'm in English.
Yeah, exactly, actually.
I propose to all to switch rename, because we can rename if you press on your image in Zoom, you can press rename and change name to English.
It's fine. I was just mentioning it's a bit different for me.
Okay, currently I changed my one, and yeah, maybe other people also do this.
Yeah, you might listen to this from time to time. I don't know what is happening today. I don't know if you are. It is the
I know that's sorry, but near to the campus of Karlsruhe is medical station. Yes.
Mm-hmm.
Yeah, I remember this noise. It's happening. It's happening often. I know about university a little bit. Okay. Okay. Alexei, I suppose that's you invite our speaker, and I suppose that you need to start our seminar because you are also organization committee. Yes, maybe let's start.
So today I would like to introduce you Mehri Shalom. She actually working on deep learning, on knowledge graphs, on text mining, and she's a postdoc in Karlsruhe Institute of Technology in Germany. Actually, we did PhD together by the supervision of the same person, of Amedeo Napoli. And I would be very happy to hear this very intriguing topic. And thank you, Mehish, for agreeing to giving this talk.
Okay, so thank you very much, Alexei, for the introduction. Yeah, thank you very much for the invitation. I'm actually very happy to be here. Just to say one thing, since I am now sharing my screen and I do not have external screen, I cannot see anything else but my slides. So if you are asking something or something, I cannot really see that. So just to start with, well, Alexei actually introduced me very well. So I'm currently a postdoctoral researcher in FIZ Karlsruhe and Karlsruhe Institute of Technology. So I'm currently heading the team, a subgroup of machine learning and knowledge graphs in FIZ Karlsruhe. So I'm currently supervising few PhD students and of course, masters and bachelors. As he said, my area of expertise are deep learning, knowledge graphs, and of course, you will also hear some things about natural language processing, but in reference to deep learning and knowledge graphs. So this, I will try to give you the overview of what actually are knowledge graphs and how deep learning algorithms are used for knowledge graphs. And then finally, I will give you some downstream tasks in which these technologies are used. So just to start with, what is a knowledge graph? This is the basic question here. So the point is here in the image you see there is person. I don't know if you are able to see my pointer. So there is one person which is connected to another person, and then one person is born somewhere in some place. So you represent the information in the form of nodes and the edges between them and the relations between them. So each node represents an entity, and this line that you see here represents a relation, but I will give you a detailed, how can I say, example on this later on. So if you want to know what does it mean to have a knowledge graph, you can also look at introducing the knowledge graph, things and not strings. What it means is that it is representing the semantics behind things. It is not just a list of alphabets which is together. However, to be more concrete on this, I would give you an example. So usually knowledge graphs are represented as I said, you have two nodes and there is a relation between them. And this relation is directed. So here in this case, this is called a subject. I will also give an example. Then there is a predicate and then there is an object. So this arrow represents the direction of this relation. So these are the two nodes. These will also be called entities, and these will be the relations. So these are usually the subjects and the object are URIs or blank node. You will also see, so URIs have like particular address on the web where you can go and look at the description of that entity or the, how can I say, more details on each entity. It's the same case here. However, in object place, you can also have a literal. I know I'm still using the words which are really, how can I say, difficult to know, but I'm gonna give you an example here. So in the rest of the talk, as I said, these nodes will be called as either entity or head or tail. So tail would be the object, head would be the subject, and then this is your relation. Now I go towards a concrete example. So I think most of you already know what is Harry Potter. So here I'm not referring to the movie, I'm referring to the book. So here you have Harry Potter, and then you have, this is a resource. This, if so there is a prefix attached to that. If you click on that, you will go to the address, but I will leave it up to you to explore it later on. You will know a little bit more about knowledge graphs in this talk. So you have Harry Potter, whose author is J.K. Rowling. So here, this is two entities which are related with the relation author. Then this J.K. Rowling has nationality, United Kingdom. So this is another entity. So this here, this is subject, this is predicate, this is object. Then this object becomes a subject, and then this is a predicate, this is a relation, and then you have the object. Now here in this case, you see something which is under quotes. This is what we call a literal. So J.K. Rowling has birth date, which is 1965-07-31. So these are called the literal informations. It can also be a description of the entity. For example, J.K. Rowling is an author who lives here, and she usually writes books on particular genres and blah, blah, blah. So this way, there can be descriptions also, which would be string literals. So I hope I'm clear about the knowledge graphs. What does it represent? So just one question. Are we taking questions at the end or in the middle?
Mehnish, it's up to you.
Okay, so I don't know, but if you have any questions so far, I think you can ask.
I think it's been pretty clear so far.
Okay, so I will move forward. So now you see that this is just, how can I say, few triples that you see. This is one of them is called the triple. So this is a very small graph you see. Then this graph can grow into a whole cloud. So this can be one domain, and then there can be these similar kind of graphs for another domain. So this has actually come together and made a whole linked data open cloud. So here you have the whole web of data, and then each of the circles here that you see represent one data source, and then each of the colors, they represent one domain. So here, for example, you have this color, I don't know what to call this. So it's pinkish, let's say, and this is user generated. So this is generated by a user interaction. Then you have gray, which is social networking. This one keeps publications or scholarly data, so on and so forth. You have life sciences, which is a pink color. So you see here you have dominant pink color, which means this data is actually belonging to the domain, which is life sciences. So here now I would tell you where these knowledge graphs are actually used. So you might have tried to search for something like, for example, Neil Armstrong here, and you might have gotten this information through Google. So this is our Google knowledge graph. So here in the middle, you have this structured metadata, which is in the form of the knowledge graph. So you have this this information, the birth date and the place, things like this. So they are connected to schema.org, but I am not going to go into the detail of that. And then you have search recommendations, which are, if people have searched for Neil Armstrong, they have also searched for Buzz Aldrin, but I think you already know what it means. So for now, so these statistics were calculated in 2017, March 2017. So it has these many entities and these many facts in 2017. And by then, of course, they have increased. So I will at some point calculate the actual statistics of this year also. So now just to give you the overview of where these knowledge graphs are actually used. So there are many companies which are using these knowledge graphs. So you have Facebook, Google. I already gave you the example of Google, Deloitte, and these companies are actually currently using these using knowledge graphs. So now after I have given you an overview of knowledge graphs, I will move towards a little bit of machine learning. So I think you already have a little bit of idea of this artificial intelligence and what are their goal. So the goal of AI is to develop machines that behave as though they were intelligent. So this is one of the quotes from John McCarthy. So what artificial intelligence covers is reasoning, natural language processing, planning. Then you have machine learning. Well, natural language processing actually uses machine learning a lot. And then you have supervised, unsupervised learning within machine learning, reinforcement learning, and deep learning. So today we are going to talk about deep learning with the knowledge graphs that I introduced in the beginning. So before doing that, I would start with this so that you get the idea of what actually are the vector spaces. So what are the embeddings? And then we will see how we are using these embeddings for knowledge graphs. So here you have an example of a vector space, which is containing words from the text. How these are learned, they are actually taking as an input a corpus, a huge corpus of, for example, Wikipedia. This is text corpus, and then they learn these embeddings, these vector representations, which are called distributed representations from these text. So what actually happens that based on that, when these vector representations are learned, the similar words, they occur close to each other in this vector space. So here you have man and woman, which are closer to each other, king and queen, which have similar meanings, they are closer to each other. Now these vector spaces can further be used for answering some questions for analogy tasks. So you have, for example, what is king plus man minus woman? So now how can we answer this question? What would be the answer of this question? I know this is clear now here, but I will just tell you based on word embeddings, how can you answer these questions? So you have this distance between man and woman, which represents man minus woman, which is the last part of this question. Then you project this vector to the vector of king. And then finally, you get what? The answer that would be queen. So this way you can manipulate vector spaces to achieve some, how can I say, achieve some or get some answers that you want. So this way, this is what we call the analogical reasoning. So now what happens here, how are these vector spaces learned? I'm not going too much into the detail, but you are free to look at this reference here if you want to see exactly how it is generated. So the learning assumption in this case is that, so you have two parts here, that is SIBO and skipgram, not parts, two algorithms for that. So SIBO, what it does, it looks into the contextual information, the context of some target word, which is not here, and then it predicts that target word. And then for skipgram, it takes this one target word, and then it predicts the contextual words. The contextual words mean the surroundings of that word. So this is the learning assumption for generating these embedding spaces. So now the problem is that many times usually there are some words which do not occur too many times. So usually if you have such words and you want to get the vector representations of that, you get this out of vocabulary problems. So now the point is, if you want to learn those infrequent words, it means that you have to really train your this algorithm on very huge amount of unavailable data. So it will be, how can I say, it will be expensive for memory to compute this kind of information. So usually the solution for this is that you represent it with the help of UNK for the rare words. But the problem with this kind of representations is that the rare words are mapped to identical vectors. So anyhow, the assumption here in this kind of embeddings is that if the words are rare, it means that they are not bringing too much semantic meaning to these vector spaces. So, actually for out of vocabulary words, there is something called fast text. So it actually automatically got changed, the slide. So what fast text does, it actually uses character engrams. So in case if some words are missing, you will get their vector also. And also it is good for the languages which are morphologically rich. For example, in French, just in case, if you have noticed that you have several conjugations of one word, so you change the ending of the words. So in these cases, you get this kind of vector. Fast text is actually working much better for these kind of languages. So what I mean by here by character engrams is that they not only learn the vector representation of student, but if they have engram, like let's say bigrams, so it takes ST, TU, UD, and so on. This the same way for n equals 4. And then this is used for only skipgram. So it doesn't use SIBO, it actually uses a skipgram model that I just introduced a little bit before. So now the question is, now you have some know-how of how vector spaces work. Now I will tell you how these kind of vector spaces or vector representations can be done on knowledge graphs, which are actually called knowledge graph embeddings. And then these knowledge graph embeddings can further be used to complete this knowledge graphs. So if you are representing something in a knowledge graph, let's say some domain about, for example, if you are representing this room or you are representing a domain of furniture. So you have a table which is white, but you cannot always represent everything completely. There is always some fact missing. And even if, so this is what is the assumption that we call the open world assumption, that not all the knowledge is always represented in the form of these graphs. So in these cases, knowledge graph completion is one of the very best things to do here. So knowledge graph embeddings are used for this kind of completion of the knowledge graph. You will also see some examples of that. And then, of course, I am going to also talk about how these knowledge graphs are used for some downstream tasks. You will also see what it is. And of course, knowledge graph embeddings will also be used for these downstream tasks to improve the performance. So just to give you a normal example, it's like question answering systems, recommender systems. Many of the current systems are using knowledge graph embeddings as a background to give some external or background information to them. So what are these actually? So the assumption is the same, that you have, instead of the text, you have knowledge graphs. And then from these kind of representation, you learn a vector space, which is then further used for some downstream tasks. Now there are several ways of developing these vector representations from knowledge graph. So you will see a few of the methods here I'm going to talk about. Then I will introduce one of the methods that we previously introduced, which is still under review, and then we move towards this part of the this picture that you see. So sorry, I should stop and ask if it is fine until now. Anyone has any questions?
Probably it is fine for the moment.
I'm sorry. We have a question in YouTube. In start of presentation, we will show definition about the edges of graph, and you use DBO and other abbreviation. After this, put two commas and no, not commas, but multi. Okay, some people in YouTube ask us about abbreviation in graphs which you used in start of presentation.
So I remember it by heart because I'm working on it for so long. So it's a
DBR.
Yeah, dbpedia.org/resource. Yeah.
Yeah.
So,
what is this?
So if you actually go to dbpedia.org/resource, you will. So this is a URI. And then if you go to this link, you will actually go to this page and you will be able to see this information. I actually didn't go into the detail of this because this is, how can I say, this is a whole lot of big conversation on that. So yeah, so you can, this is an address to this page where you can see all the information. And then using this information, you can also query it through the SparkQL endpoint, so which I'm not introducing here actually right now.
Thank you.
Yeah.
Okay, other questions?
Okay, so maybe there are no questions, but I will tell you.
Sorry, one question from on Russian. I try to translate, but I suppose you say it in the following part. How is possible to obtain new knowledge from web ontology language? How to process web ontology language and how to obtain new results and with this processing. Yeah.
So new knowledge, it's so I will talk about it actually. So many times it's like you learn from some existing resources. For example, you have text. So DBpedia that I just talked about is actually generated from Wikipedia. So what is happening there is they are processing textual information to get the information to these knowledge graphs. So it is either coming from there, or the person is manually building these ontologies or these knowledge graphs. So this is also, this is a whole area of research where different people have different perception of something. They design the knowledge that way, and then they actually, yeah, so, and then there is this alignment tasks where it tries to align the knowledge, the similar knowledge, let's say, from coming from different people or coming from different resources. So this is how it is usually done. And then,
thank you.
Yeah, okay. So I just
sorry. I suppose you finished.
No problem. Yeah, I was finished. I just wanted to mention one thing, that we currently have an online course which is on OpenHPI. There we talk about knowledge graphs in very much detail. So here I went towards machine learning, deep learning side. So if you want to know more, I can later on possibly send the link to Alexei, who can post it on the video also, I don't know. So, or you can note it down, it's OpenHPI, and possibly if you search with knowledge graphs, you will find the course. I should have added the link on the slides. Yeah.
Thank you.
Mm-hmm. Okay. I will now continue with what I was saying. Mm-hmm. So here I just say a little bit about, so there has been one tutorial in EKI 2020 about knowledge graph embeddings. You can also have a look at that. So I'm giving the references on the bottom of the slides. You can always go there and look for more details. So there are several algorithms, as I mentioned here, that you have node embeddings. In this case, where these graphs are considered as node arc graph, there you have node with some edge, which is some relation which is not labeled to another node. So here you do not have labeled and directed information. So what you do in order to generate vector representations from there, you use node to vec, deep walk, and line. I'm not going to go into the details because the focus of this talk is knowledge graph. So the similar way you have graph neural networks. So the examples of such node arc graphs are, for example, citation networks. So one paper cites another one, then this paper cites another one. This way you get a whole network, and then you can generate vector representations from there. So this is just to give you a little bit of information that there are other types of graphs which also exist. And then we have knowledge graph embeddings, which is what we are going to talk about now. So there are many ways to generate knowledge graph embeddings. There are translational distance models. So each time there are the scoring functions which are changing, and then there are different types of ways to generate this kind of information, this kind of knowledge graph embeddings. So they can be without literals, they can be with literals. So but don't worry, I'm not going to go into the detail of all of them. I will just try to give you a know-how of how these are generated. And then you have several methods to generate this, building one upon another. So here I will start with the translational distance model. I will also give you an example. So what it does, it uses distance-based scoring functions, and then it measures the plausibility of effect as the distance between the two entities. And this translation is carried out by a relation. So there are many translational models, trans-E, trans-H, and they are improvement from one over the other. So you have a whole survey of these knowledge graph embeddings. You can go and have a look at that. I will give you a little bit of introduction on these translational models. So what actually it does is it takes the knowledge graphs and projects it into a vector space. So this is the idea behind a knowledge graph embedding. So what happens here is that entities and relations, as I said, that subject, predicate, objects will be represented as head, relation, and tail, as I said before. So entities and relations are embedded into the same vector space. And then the relation is considered as the translation. So here, if you sum up the vector of head and the relation, then you get the tail. So you have this kind of information. So for example, I will not look in on the second part. Let's see here. If you have sky tree location, then it should automatically give you Tokyo. So this way, this is the learning assumption for these kind of algorithms. Now the problem is that the entities which are not very related to each other might also occur close to each other in this kind of assumption. For example, Skytree location, Tokyo. Here you see that the tail entity is the same as this one. Location is the same. Gundam and Skytree are actually not similar to each other at all. So you can actually look it up. This is some building and this is some character, I think fiction character from Japan. So these are completely different, but they will occur close to each other, which means it is not it is only considering one-to-one relations, but not one-to-n relations, meaning that one entity can have different roles for different relations. So in order to solve this problem, trans H was introduced, in which there was a hyperplane of the relations which was introduced. So the head entity and the tail entity were projected to that hyperplane. So in case if you don't know what is hyperplane, it is a sub vector space in a vector space which has dimension less than the actual dimensions of the whole vector space. So this is our hyperplane here, where the relations are projected. So here, each entity, the head and the tail, are projected to this hyperplane of relation. The translation is conducted here, and then the tail entity is given in case if it is H plus R, which gives you T. So this way they improved this problem of one-to-one relations. And then there is another increment over this this algorithm. In this case, they have generated separate entity vector space for entities and separate vector space for relations. And now the same thing is happening, but head and tail entities are projected to the other relation space, and then the translation is conducted. So the point is that this way you have several translational models that I just told you before, and then they are improvement over the other one. And this way there have been a lot of studies since 2015 up until now that are improving knowledge graph embeddings, trying to improve the semantics that are coming from the knowledge graph to the vector space. So I will introduce one last model here, and then I will take the questions on this. So there is another method which actually generates knowledge graph embeddings, that would be RDF2Ec. So what it actually does is it generates sequences from these knowledge graphs as in natural language with the help of GraphVox or WL subtree RDF graph kernels. I will not talk about them. I will just give you an example. And then they use word2vec for generating vector representations. So just an example here of GraphVox to give you an intuition of how that works is that, for example, you have an event which has objective influence. So the relation here is inherits from. So it starts the walk of depth 3, event, objective influence, transitive action. So you can see here, this way it generates sequence out of these graphs. And then you have depth 3 again. Let's say it is starting from intentionally affect, then invasion scenario, and then conquering. So this way, the sequences are generated doing random walks of any depth, but here I show you an example of depth 3, which are then given to word2vec, and then they generate similar vector spaces for the graphs. So this is what I explained here. So I already showed you word2vec, and that's it. For now. I will stop to take any questions, and then I will, I think, move forward.
I would probably start with a question.
Yeah, sure.
Actually, you show how embeddings works, or what the ideas behind these embeddings. But there's two kind of questions related. So how is it used?
Mhm.
And more or less related question, how it is evaluated, how the quality is computed.
Very good question. So you asked the future thing. So I'm actually moving towards that. So you have to wait a little bit on that. So they are actually evaluated on link prediction. So that this is what I'm going to talk about later on. So I think you should wait a little bit. Yeah.
And for usage,
Sorry?
how it is used? Only for link prediction?
No, actually, so these vector spaces are then used for example, recommender system. You will also see one in mine. I will share one of my works and you will see how it will be used. So what do they do? Usually they try to use external knowledge from these knowledge graphs. So it could be domain specific. It can be something else. For example, sometimes in robotics, how do they use, or in image recognition, let's say. What do they do is that they use concept net, which keeps the common sense knowledge. So for example, in image recognition, how would it help? Is that in case if it recognizes a scooter, let's say, then the thing on top of the scooter would be a person, should be a person. So this kind of knowledge they can already infer from this knowledge graph and try to say that the next object that they want to recognize would be a person. So these kind of things. Then they are also used for example, I'm going to talk about one of them. I use knowledge graph embeddings for co-reference resolution also. And then there are many natural language processing tasks where the knowledge graph embeddings actually help. Yes. I hope I answer your question.
Yeah, thank you.
Yeah.
Excuse me, I'm asked questions from YouTube. One on English, I write it in chat. How knowledge graph techniques, various logics, reasons, so on, are combined with deep learning within applications. Knowledge graph are just data for DL algorithms or not?
Okay. So, so about the applications, I think I already discussed right now, how can they be used? So knowledge graphs can be treated as a background information, like they are representing the whole knowledge about something, of course. Then there is knowledge representation and reasoning, which I'm not discussing here yet. So there is reasoning where you infer, you do this deduction and then you infer that this, how can I say, for example, if objective influence is an event, so I'm just twisting the example a little bit. So and transitive action is an objective influence, it would mean transitive action is an event. So things like this. This way, if you go through this path, you can also reason like, if conquering is invasion scenario, then you move on and then you can also infer that this is conquering is also an event. Well, conquering is actually an event, so yeah. So this way you can also infer this kind of information from knowledge graphs, from ontologies actually, yeah.
Thank you. Another questions I translated from Russian. How edges, labels written on graph edges are used in vector spaces?
Yeah, so they are actually represented as it is, the relations also. So the same way as in word vectors, you have the same thing as in knowledge graph embeddings. So the relation, for example, here precedes, there will be one vector related to precedes in the knowledge graph embeddings.
Okay, thank you. We have no questions in YouTube more. Maybe some people want to ask in this chat. I know that's Kirill Yurkov work with such type of
Konstantin, I have a couple of huge questions, but they are much better asked at the end.
Okay, thank you.
Okay, so I will then continue with what do you use it for. So now these knowledge graph embeddings are computed. What next, as Alexei asked. So now we can evaluate it on different things. You can evaluate, so there is in KG applications. In KG means that within the knowledge graph, you are trying to complete some information. So you have, for example, triple classification. So this subject, predicate, object is called the triple also, as I said before, but I'm just repeating. So for example, you have to tell, it's like binary classification. If Joseph Fourier has occupation physicist, yes or no. If it says yes, it means that this triple exists. So it will be like true. And then if it says no, then it means this is not true. So this triple is wrong. So here, along with saying yes and no, it also tells you the confidence with which it is giving you this answer. Then it can also help you in doing tail prediction. As I said, this H plus R equals T. So you have Joseph Fourier, occupation, what? So it can give you with confidence physicist 0.95, chemist 0.93. So physicist is the highest choice, but of course the difference is not so high. Then you have head prediction, where you have to predict the head of this triple occupation physicist. So it will be Albert Einstein, Stephen Hawking. Of course, it is not just Joseph Fourier, so there are going to be other scientists here also. Then in relation prediction, you have given the head and the tail entity, and you try to predict the relation. So it will be occupation in this case. So these are examples, of course, to make you understand how what does it mean. And then we have entity classification, where it determines the type of an entity. So Joseph Fourier is a person, and then Joseph Fourier is a human. So yeah. So these are the places where you evaluate them. So this is what I just said, that these kind of link prediction tasks are the in KG applications. Then you have out KG applications, where you have where these knowledge graphs are used, like in question answering, recommender systems that I have been saying before, but I think next time I should add a few more other studies which are, telling you. So in case if you want to have a look, so there is a new recommender system which is recently published in 2020, which is called KRED. This is a news recommender system, and it is using knowledge graph embeddings for recommendation, along with the textual information from the news articles to make these recommendations. So this is, this is what I can give you as an example, and you can look for this paper. So for these knowledge graph embeddings, already there are libraries which are existing. So you have PyTorch, Big Graph, you have PyKeen. So PyKeen is actually now growing from time to time. So they are adding more and more algorithms there. Then you have AmpliGraph and OpenKE. So you can note down the names, and if you want to play around with them, please do. So, okay, yeah, okay. So now the point is, until now we talked about only the structural information, where you have subject, predicate, and object. But what about literals? We haven't used this information at all. So here you have this literal information. Now there is a whole group of knowledge graph embedding algorithms which improve these representations with the help of the descriptions of these entities or the literal informations which are there. So for example, if you look at only this, let's first start with this. Then in the vector space, Kate, Abel, and Hannah should actually occur close to each other because all of them are connected with the same relation to the same class. So sorry, same entity, same tail entity. So Hannah plays sport, Abel plays sport, Kate plays sport. But what if we take into account this kind of literal information given about them? So this is, for example, Kate is a female, Abel is a male, and Hannah is female. So I'm just considering one for the sake of simplicity. Now, if you consider this kind of information, then Hannah should be closer to Kate as compared to Abel. Same is the case with the birth here. Kate and Hannah should occur together because, sorry, the other one appeared, I will go back. So Hannah and Kate should occur together because their date of birth is closer to each other. So now if we have another entity which has, let's say, mark male, it would be closer to Abel as compared to Kate and Hannah. So this is just to describe you the problem that in case if we do not have literal information, there is a possibility that we are missing out on some information, some extra information that should be included. So for doing that, we have several types of literals. We have short text, we have longer text. So, and then we have numeric literals, we have image literals, audio files, video files. So there are many kinds of information attached to each entity. So for example, you have a duck, this is one entity, and then there is an information which shows you the image of the duck. I know it sounds like, why do you need this external information? But it actually helps just in case if you want to say that the duck is an animal or not. And you will see when these knowledge graphs are generated automatically, sometimes they get these wrong types. So in these cases, you can use the image information to correct these types of these entities. So we have also done some studies on that. So you can look it up. I think I would mention one of them, but yeah, it is called type prediction. Yeah. Okay, so I just went away from the topic a little bit. I will come back here. So you have several types of literals, which will help give you more information about each of the entities and possibly improve the semantic representation of these entities in the vector space. So here I will try to go through a little bit faster. I have a feeling that everybody wants to see the applications of these knowledge graph embeddings. So, so there is for knowledge graph embedding models which are taking advantage of the text literals, there is extended RESCAL. There are several approaches for that, which are using, for example, SIBO or CNN or AGRU for multilingual knowledge graphs. So there is a whole area of research on that also. So they use this information to get the representations of the text, and then they combine it with the representation of the knowledge graph. So by representations, I mean the vectors of these entities with the vectors of this text, for example. Then there are many of them which actually use numeric literals. So you have, they use binary classification and regression techniques and probabilistic product of experts and linear regression. So this way also they follow more or less the same principle, and then they use this numeric information to improve this entity representation in the vector space. Now there are several drawbacks to that. So you can have data types that you need to consider. However, recently we also worked on that, and we tried to normalize the data knowledge graphs before we give it to the knowledge graph embedding models. So there is still some work going on there. And then the other kind of literals would be images and multimodal, where you have numeric information with the text information, or numeric information with text information and image information. And then you have the same evaluation tasks. You just add extra information into these into the representation of these entities, and then you evaluate on the same tasks as link prediction, triple classification, and entity classification. And now I come to the evaluation part. Okay, so here several data sets have been proposed for, these are the benchmark data sets which have been proposed for evaluating link prediction tasks based on knowledge graph embeddings. So one is Freebase, which is a cross-domain knowledge graph. Then you have, for example, DBpedia also. You have Wikidata, you have several cross-domain knowledge graphs. So DBpedia, for example, is generated from Wikipedia. Wikipedia is also cross-domain. So there are several data sets for this. We have currently just, so this is under review, but we have currently also generated a data set from Wikidata for this kind of link prediction. But coming back to the point, I will talk about two data sets here. So these are FB15K and FB15K237. By 15K, it means it has 15,000 entities there for which they keep the tribal information. And then they divide it into train, valid, and test. And then they compute for tail prediction, head prediction, or both head and tail prediction. So if you look at this survey, we have all the algorithms there, which are implemented and compared to each other. And I'm just adding only few of the results here. So here in this case, for example, DisMult is one of the algorithms which considers literal information, and it is performing the best for hit set 1. So for hit set 1 means you saw that I said that in link prediction or head tail prediction, it gives you this confidence. So hit set 1 will take only the first one, which is ranking the highest, and then compare it with the ground truth. And this way you get this evaluation. So the same case with the head tail prediction and relation prediction. Are there any questions?
I have some of them.
Yeah, yeah, continue.
Yeah, actually, probably it was a bit long ago, but still, the libraries you showed, you remember? Is it about like learned deep networks? What does it mean, library?
So for example, so just tell me if I can relate to this with you on this. So you have, for example, these TensorFlow libraries for BiLSTM, things like this. So this is the similar kind of library which is implementing all these algorithms. So it helps you in creating the data sets also. In creating your own data set, like you can give your data set to them, which is in the form of a knowledge graph, and it will generate this train, valid, test also. So AmpliGraph, I played around with that. And then you can just, you can apply trans-E or whichever algorithm you want to use. So it is all done.
Okay, but the weights of the neural network, is it available? The weights.
So parameters. Yeah. So for that, actually, yes. So this is one of the things that always gets takes a lot of time. So it's like hyperparameter tuning. So what one of the libraries, AmpliGraph, provides this grid search. So it tries to it computes the hit set 1, for example. I'm giving you just an example for each for combination of parameters, and wherever it performs the best, you can choose that parameter for training the knowledge graph embeddings.
Yeah, but somehow is it useful? You know, like in text mining or BERT, usually you start from a more or less learned model, not from the scratch. Is it the same in knowledge graph, or when you take, or it doesn't make sense to do this?
Yeah. So yes, that's a very good question. So actually, you can. So if it is already pre-trained somewhere, you can just take it and use it. It's I don't think it should be an issue, because most of the people use trans E on knowledge graphs. So I think it should be okay.
But are these weights available like for DBpedia?
Pre-trained model. Yes, I can send you. So for the pre-trained model for DBpedia are available with the help, which are generated with the help of RDF2Vec. So I can send you, yes, there is the work by University of Mannheim people, and they have made it available, yes. And we have used the pre-trained models already in some other.
Yeah, thank you. And actually I would return to basically to the slide you have. And the question is actually, there is some numbers about like, let's say precision, accuracy, or other metrics. But is it good? They can be, of course, used to compare two models. Okay, but is this good numbers now, or it is a bad numbers?
So here, yeah, I know why you are saying that, because it is like 0.4 and 0.5, which is pretty low on its own, but this is fine. This is good, actually. Yeah. So here, what you see is, how can I say, I will tell you. So in these papers, they have shown that, for example, if you have trans EA, let's take an example. This has proved to get better hits at 1 as compared to trans E. So and then here you see like the last models until 2020, which have done these experiments with the knowledge graph embeddings with literals, and these are the highest numbers that you see. So these numbers are fine, yes.
So for practice, it's fine to have the numbers like this.
Yeah. Yeah, so sometimes in the actual knowledge graphs, like, so these are the benchmark data sets. So there are some knowledge graphs which are not really, how can I say, tailored for this. Either you have to tailor them, or otherwise you get the even lower numbers than this. Yeah. So when you, of course, take into consideration what should be considered for these benchmark data sets, then it gets a little bit higher than, yeah. So this is fine, the numbers.
Okay.
I'm sorry, but I want to pile up on that question because it's extremely important for me as well. What we mean when we ask are they good numbers is, let's say, the result which is generated, how close it is to a human, to a professional who is actually building a knowledge graph by hand versus something that's generated, even at this point, without talking about any downstream tasks at this point. How good are those results? Are we yet at the results which are nice and interesting, but not really human level yet? Or are we talking about something that is actually at the level of professionals, or even surpassing them?
Yes, that's actually a very good question. So if I'm understanding you correctly, you want to say that if we do these kind of completions, if a human does that, then what would be of course it is going to be better, but to just let me say one thing here, that these data sets that are generated, so it depends on how they are generated, of course, and then you are taking this data set and you are dividing it into train, valid, and test, which means you have the actual links that should be predicted already in the data set. So it can be manually generated, it can be of course, automatically generated. But if it is automatically generated, then there is the propagation of error of the automated generation. This is first step, which is not going to be accurate either. And then there is this, how can I say, these are, then this algorithm also creates some, which is not perfect, of course. Yeah.
Thank you. That practically was my first question a bit later. Should we move on? Because I have a couple of questions more, and I don't know how much material do you still have?
Okay, so I will try to go fast. I have a feeling that I already passed my 1 hour here. So I will just talk, I will now move on to my research that we have. So we recently had our own algorithm for generating this. This is just to give you a know-how of what is happening in our lab. So the point is that this algorithm is still under review in the journal. So what it is actually doing, it is following the line of using literals for knowledge graph embeddings. So for example, here it is going to use the textual literals, the description of each of the entities. So you have already a knowledge graph which says Titanic has a star which is Leonardo DiCaprio. It is a movie. Then Inception is also a movie. However, here the missing information is Inception and Leonardo DiCaprio are not connected. However, Leonardo DiCaprio is starring in Inception. However, this information, even though if it is not there, so just to tell you again that DBpedia, so here you asked me, this is DBpedia resource, this is DBpedia ontology. So DBpedia resource has the entity here, and the ontology represents the class. So here, for example, Inception entity is of type movie. So here you have this DBpedia ontology. Okay, anyway, so let's move on to what I was going to explain is you have this information that Leonardo DiCaprio is starring in Inception in the form of this description. So it says here the film stars Leonardo DiCaprio. So what we do in our case, we use this kind of information to predict these kinds of links here. So for this, I will just give you overview. I will not go into the detail of this. If you want to see the details, you can look at the paper. So what we actually did, we took the descriptions and so of course there are more things here, but I'm going to just give you an overview. So for first, we generated paths from these entities so that it keeps the contextual information of the entities. And then we generated vectors for these paths with the help of attention encoder and decoder. And then we took the descriptions of each of the entities. So these paths are generated starting from the head entity. So we go towards, for example, so if we start from Titanic, it goes Kate Winslet, and then it goes person. So actually this sort of, so this is not a good example, I will come here. So Whole Truth has a writer, Philip Mackey, alma mater, and this way you have path of some certain depth, as I discussed before with the random walks. And then we generate vector spaces, vectors of these paths there. And then we use the description of the entity with the help of SBERT. And then we combine all of this information, and then we generate the knowledge graph embeddings out of this. So this is yet another improvement over the existing algorithms. And then we evaluated on the link prediction task. So here you have triple classification. Link prediction actually here includes the average of head-tail prediction. So here we see that we obtained good results with that. And yeah, so this is one of the works that we just did, and it is under review in Semantic Web Journal. So this is just to give you one example of what is happening in our lab. And then I come to the point of knowledge graph embeddings for downstream tasks. So just let me. Okay. Sorry. Yeah, please.
My question, actually, why multiplication of two embeddings?
It is the inner product.
Yeah, but,
Yeah.
but I mean, why this kind of operation is selected?
Because these are two different things, you know, so the vectors were obtained through different kinds. We can discuss this if you want offline. So this is actually like, we just finished this model, so we will, I have given this information somewhere, yes.
So it's concatenation in a sense.
Mm-hmm.
Okay.
Concatenation is a plus, actually. So this is inner product, yeah. Mm-hmm. So in a sense, yes, it is combining that information.
Okay.
Mm-hmm. Okay. Okay, I will come to this this part now. So I'm not so far away from finishing. So just let me know when the time is over, and I will wrap it up faster. So this is a little bit older study that I did in 2017, which is about NLP, which is using knowledge graph embeddings for knowledge reconciliation. Actually, it's co-reference resolution. So yeah, this is an application of knowledge graph embeddings, but it is of course doing something else. So let's dive into that. So the idea of knowledge graph reconciliation, knowledge reconciliation here is that you have two, let's say, slightly different knowledge graphs, which are representing similar kind of information. And then you combine it into one knowledge graph and then provide this one knowledge graph as a consolidated view over two texts. Now, here I say two texts, but it can be several. So it is sort of a summarization of whatever is happening into one knowledge graph. So the idea, the overall architecture behind is that there is text on which we ran some tools which generate knowledge graphs out of text. And then, as I said, they are talking about something similar, but they can still be different from each other. For example, the second graph could have newer information as compared to first, but still there are some overlapping information. So we reconcile them into one knowledge graph. This can be used for text summarization. Actually, before you combine them, it can also be used to compute the similarity, but we haven't evaluated directly for document similarity. So this tool was built on top of the existing tool, which was doing similar thing, which was based on graph compression and alignment, but it uses string matching to align the two knowledge graphs. So if you want the details, you can go here, but I'm going to give you the overview of this framework in the next slide. So first of all, the first task here is to generate knowledge graph from the text. So there are several ways to do that. The one that I'm talking about here, it uses CCG parser along with the first order logic. So what happens is that you give as an input text and it generates first order logic. And these first order logic is then converted into RDF triple. So yeah, it's a little bit, how can I say, I haven't talked about logic here, but this is the overall idea of generating these knowledge graphs in this tool at least. So why do they call it event oriented? Because it keeps event as the head, as the root of this knowledge graph. So you can see attack is an event, which is a verb, and this is the root of this knowledge graph. So based on the contextual information, it actually connects this attack to some entities. So you have, so the point is that first it generates the knowledge graph from one text. This is Spaniards attack the Incas. So in the purple, what you see are the things coming from the text. So you have attack. Who is attacking? It would be Spaniards. And this is just the determiner. And then it is Spaniard, but there are plural. So it has quantifier, which is multiple. And then who are the Spaniards attacking? These are the themes. So this is VerbNet, but I will not go into the detail of that. So this is the theme, which is Incas, which is the same as Inca Empire. So this actually also directly connects this Inca to a DBpedia resource. And then what happens is that based on the mappings that the cloud that I showed you in the beginning, they go from DBpedia to schema.org. The mappings already exist and they enrich this graph with this kind of information. And this way they know that this is a place. So this is how the knowledge graph is generated for a text. And then just to give you a brief overview for doing this reconciliation, we use this Framester, which is a linguistic linked data cloud. So the data cloud that you saw, there is one portion which consists of the information from linguistics data. So for example, one of which is the VerbNet here, which you see here also. So this way, this kind of information is present in this linked data cloud. What I do in this application is I crawl this and generate embeddings out of this. So with this way, I have embeddings for the nodes as well as the relations here. So I can explain this linked data cloud later on if you want some information on this. So this is actually the paper which is connected to that. So this is, sorry, 2016, I will correct it. So this is the overall view of what is happening. So I introduced you everything, but now how these things are used here. So you have two texts here out of which we generated the knowledge graph. And now the question is, how do we create links between them? To do that, we use the embeddings from this linguistic linked data, and then we compute the cosine similarities between the nodes. And of course, we consider the path information also. And then this way we have all of these connections which you see in colored here. So finally, you will get one reconciled knowledge graph out of these two pieces of information. So we evaluated this. I'm still staying broad, but yeah, I can go into the detail maybe later, but yeah, you have the paper for this also. So we evaluated this on cross-document co-reference resolution. So what co-reference resolution means, it maps similar entities in two different texts with the help of, so it just, how can I say, creates links between two similar entities in two different documents. So there are also many of them which do on multiple documents, of course. So this approach is actually generalizable to multiple documents also. So, so there are several ways to evaluate this. So you can Google the definitions of each of these metrics if you want. So in most of the cases, so this is the baseline, and we tried different variations here with the help of frame to vec, role to vec. So role to vec is this theme and agent kind of roles that I was talking about. And then finally, we saw that most of the time, well, not most of the time, in all the cases, our variations were performing better with the help of knowledge graph embeddings, except for one of them, because this is, so this was sort of considering taxonomical information. So Wu Palmer is performing better on Blanc. So yeah, so this is one of the applications. I hope it was not too much technical on this, but yeah, this is where we use knowledge graph embeddings for generating vector spaces from some other kind of resources, not just text. And then in one of the studies where we performed short text categorization, and this is the last one I talk about. So here I will also just tell you why short text is a bit of challenge. It is everywhere. You know that you have conversations, you have news articles where you get like one line of description that yeah, this is what the news article is about. Then you have social media like Twitter. You have a limited number of characters that you can use to express what you want to say. So what happens in these short text, you can have several kind of ambiguities. So for example, if a person is saying, call me a taxi, then the other person can be confused. Do you want me to call you taxi or you call you a taxi, you know, by call you taxi by name, for example. So in these cases, in these kind of ambiguous cases, it is good to know the contextual information to understand what the other person is actually talking about. So for example, another example, which would be more easy to explain, would be Floyd revolutionized rock with the wall. So here we have ambiguity, we have lack of contextual information, and you will see how. So let's completely show you so that you can easily understand. So Floyd is of course Pink Floyd, but here rock can mean a rock, then rock music, or it could be Dwayne Johnson. And then you have wall, which is defensive wall, Berlin Wall, the wall. So it could be anything. However, with the help of disambiguation, named entity disambiguation, you can know that Pink Floyd revolutionized rock music with the wall, which is the album. So in these cases, the entities help in reducing the ambiguity. So in order to classify this kind of short text, we proposed wide and deep model. So which is actually the actual model is proposed by Google. So here, since it is weakly supervised, I will just tell you the overall view here. We first generate the training data, and then afterwards we use this generated training data to do this classification using wide and deep. So wide usually uses linear models, and the deep is using entity, category, and text embeddings. And this way it is performing short text classification. So these are the results. For, as usual, you have 3 data sets on which you can evaluate. So you have AG News, snippets, and then there is a DBpedia and Twitter data set. And here you can see that wide and deep is performing better in all of these cases. So, okay, now I will wrap up so we can start the question answering again. So what did we see in this whole talk? We saw a brief overview of knowledge graphs, and then we talked about knowledge graph embeddings with or without literal, and then how can they be used in the downstream tasks using knowledge, in the other downstream tasks for natural language processing. Then what is happening nowadays is also evolving knowledge graph embeddings. So you have also temporal knowledge graph embeddings where they are considering the temporal information of the contained in the triple. And then there is more how can these knowledge graphs be used for explainability and explainability in knowledge graph embeddings. So these are the topics which are ongoing, but this is not the part of the discussion of this talk. So yeah, you can of course explore on your own about this. And thank you very much. I'm finished.
Okay, hello. I'm sorry for small delay. I tried to open. We have one question on YouTube, which was not answered. Could you clarify, if we are interested in nodes A and B, then all other nodes connected with them are considered as literals? I write these questions to chat.
Yeah, I think I should. No. So I don't know if you are, so literals are usually, so you see that there is one structural part in the knowledge graph where you have For example, table has color blue. So you have these kind of entities. Then blue has type a color, these kind of information. Literals are giving you extra information. So maybe I can share the screen and give you the example again that I introduced in the beginning. Here. So you see these are under double quotes here. It can also be a whole description of something. So usually when you go to these DBpedia pages, they also keep the abstract of each of these entities. So for example, for Harry Potter, it will be like, it is a sci-fi book which is written by J.K. Rowling, and it is, how can I say, famous among the children or things like this. So usually this abstract is the first paragraph from Wikipedia. So this kind of information gives extra information about an entity. So these are literals, which are here, but they are different kinds of nodes. Is it clearer?
Thank you. And some questions from me. I have some experience with gain-set enrichment analysis. It's method when we take expression data about, for example, you have two cells. One cell produce some proteins and other produce some others, and you compare it and draw a graph or how expression of some proteins or enhancer influence on other. And when we have this graph, we try to enrich this graph with some information from several from articles, from information about for example, some tables about genes and disease, and other information. And after this, we try to explain what's happened. Do you have experience with such kind of application? And what's the state of the art, not from biological point of view, but from your areas, yes, in these fields of studies?
Yeah. So so as far as I know, so I am not very much biologist, let's say, but from what I know about this protein graphs that I have seen in these kind of studies, they are protein-protein interaction graphs. And
yes. One of this is protein-protein interaction, yes.
Yeah, exactly. So they have tried to do this link prediction on them also. I can give you the links to these studies. So they have used it for graph neural networks. So yes, they have tried that there. The point is, again, they have tried it. They have taken this data that you are saying about protein-protein interaction, and then generated this benchmark data set out of it also. So yes, it is applied there. Also, it is applied for drug-drug interaction in the knowledge graph embeddings. I can find the studies and I can tell you about that. But I have no first-hand experience on that, to be sure, just to be clear. Yeah. And if I'm understanding correctly, with the gene expression, you have it in numeric information, if I'm correct?
There are several there are several different analyses. Some of analysis proteins, and we have labels as proteins. Some analyze expression, and we have orientation on the edges, and many others. Any types.
So yes, so the point is that nowadays many people are trying to apply them to the real world scenario instead of just the benchmark data sets. And they have tried this with gene ontology. I don't know if you know about that, but for gene expression data set, I haven't seen yet. At least to my knowledge, I didn't see the study, but that would be interesting to see, I think. Yeah.
In any case, thank you very much. Thank you for answer. Okay, we are waiting some questions. Are you finished with the main part of presentation, or?
Actually, yeah.
Yeah. maybe you say some words about application, how we can use these graphs in classical machine learning problem, for example, text classification and so on.
Yeah, so this was my last study about, so I think I went over it fast because it was a lot of time that I took to explain all of this. So we used entities from the knowledge graph, and then we generated the network out of these entities. And then we use this information along with doc2vec and other kind of vector representations. And it's, how can I say, at the end, it was more like combining this kind of vectors with the vectors of text, you know. And then this way we did the classification. So yeah. So this for this one, it was this way. And then for the Framester that I was talking about, I crawled this knowledge graph, linguistic knowledge graph, and generated these vector spaces from that, which I then used for computing similarity. So it depends on what you want to do at the end, you know. So for the classification, we used it that way, yes.
Thank you.
Can I hijack this seminar for like 10 minutes?
Mm.
Because I have a couple of rather large questions. And is that a problem?
No, fine.
I suppose time is not a problem because all people which should finish are already finished. Yeah, we have time for discussion really because it's very important topics, and if some people can't look now, they will open translation, open our records and finish in other time. Yeah, yeah. Let's try discussion.
Okay. So first, I want to start with an apology, so to say, because well, I am a researcher, but also I am a CTO in our small company, and and for the last couple of years, we had several projects where we discussed using knowledge graphs, and every time I was very strongly against using them, quoting that they're not production ready. So I'm here because I hope you will prove me wrong, so to say. So yeah, I'm the worst kind of listener, one with preconceptions. So anyways, my first question. Let's say we have a relatively small domain. And I mean relatively, meaning that we still can find hundreds or maybe even thousands of documents which describe it. So it's something that is well covered by the internet, but it's very specific. What it means is that we can't really hope to have useful knowledge for this domain that is already in DBpedia, for example, or even in Wikipedia. It will be too shallow for our practical applications. So in that case, how hard it is nowadays to build a good, practical, and useful knowledge graph?
That's a very good question. So I will tell you from what is happening, what projects we are working on currently. So yes, DBpedia, Wikidata, Freebase, all of them are really cross-domain. So if when you go to a particular domain, it gives you some part of it, but nothing, not more. So we are currently doing some things with, so there is actually one project where the knowledge graph is being built for material science domain. So you have to have really active collaboration with the experts to understand. So it's an effort. It's not so easy. Yes, I agree with you. So we are really actively collaborating with them to understand. We cannot be material scientists, you know, so we are ontologists. So we have to really understand their point of view of the things and then model. Sometimes we try to give them tips to model, and they try it on their own, and then they confirm with us if they are modeling it right, you know. So this takes an effort. Yes, I understand that, and this is happening. Then the other part where other application where we are currently working is the domain of cultural heritage. So in the cultural heritage, at least there are many existing ontologies. So now what usually happens in the process of generating knowledge graph is you have to take what you have, to design it, and then to connect it what is already existing out there. So for example, with material science, we have not too many ontologies, not too many knowledge graphs which are out there. But we build from the domain that we have, like application ontology, and then we connect it to the others. And this way we sort of do the interoperability. So you use the external information from there. And then the other way to do it is, for example, I think Konstantin was also asking this, but sorry, I didn't answer you on that. So if you have this scholarly data, you can generate knowledge graphs out of that also. And there are, by scholarly data, are these articles which are describing some things about a particular domain, or for example, artificial intelligence, computer science, mathematics, material science itself. So there are tools which are now available, which are using, for example, which are using these embedding technologies, like I would say BERT embeddings, for generating triples out of these textual information that is given in the scholarly data. So yeah, so there is this kind of information. So it depends on what source you want to use. I know when you are doing it with experts, it's a lot of effort to do that. Yes, and yeah. So there are several ways to look at this. Yes. Mm-hmm.
Yeah, about the second way. I've read the articles, I've seen some of the results, but in your own personal opinion, how much fine-tuning do we need to do on that second way of automatically generating something from scholarly articles to make the resulting ontology or knowledge graph really applicable to practical tasks?
Yeah, so yeah, that's another good point, because for example, when you want to train, for example, BERT model, which should be used for some algorithm, training is really costly. So you need to have really amazing servers to really do that. So yes, you have to fine tune. But so for now, in my experience, what I have seen in front of me, they are starting to publish more and more domain specific BERT models. So I know there is SciBERT. I'm just giving you some examples. SciBERT, we are currently also working with the mathematical scholarly data. So there is MathBERT now, which just recently came. Then there is BioBERT. So they are trying to do it domain specific, but let's see how many domains they can cover. Yeah. So yes, this can be a little bit expensive, but you then need to sometimes do this transfer learning kind of things. So yeah, you have to sort of, how can I say, merge some of the technologies to get what you need. Yeah.
Yeah, so yeah, we have had some experience with that as well, mostly with Bluebird and Biobird. Yeah, thank you. That was the first question. The second question, can you go to slide number 57? I think it will be easier this way. So while you do that, the question is about how useful are knowledge graphs as a, so to say, intermediate results. So what I want to talk here about is, we all understand that knowledge graph can be given as an input, and that's additional domain information. That's okay. But here you are getting knowledge graph as an intermediate result, because actually in the end, you want to have coreference resolution, or in fact, coreference resolution is actually in an intermediate result itself, because at the end, you will probably want fact extraction. Or another example which we gave is text summarization. Text summarization can be a final task, and for it you can as well use the reconciliation which you are using here. So my question is, as an alternative to what you are talking about here, I give just use text embedding. Just embed a couple of texts, reconcile embeddings, don't think about graphs at all, because graphs are useful only for people. For machines, we need vectors. Mm-hmm. So, and that's kind of a counterpoint. And yeah. So back to the question, why do we need graphs as an intermediary result?
Mm-hmm. I understand. So your confusion completely. So the point is, when we are generating knowledge graphs, we are actually also connecting it to the external resources. For example, this named entity disambiguation that I talked about. So it is very good for dealing with ambiguity. So they are also they can be helpful here. For example, I mean, this is a very simple example, of course. So you can actually see that here you also get these types of the information that you are getting. So I think it would actually help in getting the structured information out of the text, along with the type information and the extra information that you can get. And also, for example, if you connect to the DBpedia entity something, then this entity has its own description. You can use that information. Of course, again, it has, I mean, I'm just talking broadly. So yeah, there is, how can I say, it needs to be proved that you need to take this description information and then use it with this kind of information and try to see if it performs better. So yeah. Here, for example, anyway, I will tell you that Mergilo, that the tool on which it is based on, was actually doing this kind of knowledge reconciliation. It was comparing it with the co-reference resolution of the text-based methods. So this is like incremental on top of that. So yes, I should have included those results also too. Yeah. Mm-hmm.
Yeah, so as a counterpoint, every time we go back to the graph, we are losing some information because, well, probably, so you're probably right. The best way to judge it is by the results in the downstream task. And what you're saying is that results are better, right?
Mm-hmm. Yeah.
Okay.
Mm-hmm. So that's yeah, in Mergilo it was shown, so we didn't bother to go back to the results of that, you know, so. Yeah, but that's a very good point. Actually, I should have, but yeah, I didn't know this question was going to come up. So, yeah.
Okay, I understand that. So, yeah. Because just to add my couple of ideas here is, when we've discussed it in our own team, I've actually said that, no, let's use embedding, because the only useful thing about graphs is ability to understand what's going on in our pipeline. If we have a complicated pipeline of embeddings, neural networks that use embeddings, and again embeddings and stuff like that, then we have no idea what's going on. But if instead of embeddings, we will have knowledge graphs, we will be able to understand what actually is going on in our pipeline. Mm-hmm. That was one point of our discussion. Have you ever heard about anything about using knowledge graph embeddings, or more specifically, extracting knowledge graph embeddings from results of the neural network to understand it better?
So you want to know, okay, so maybe I'm not understanding your question,
okay,
right? Yeah.
Let's me put it the other way.
Yeah.
We have two options. First option is we just generate an embedding and give it to downstream task. That's one pipeline. Another pipeline is we generate actually a knowledge graph and give it to the pipeline. And the second one is superior because we can use the knowledge graph as a way of explaining what's going on. Have you ever seen any kind of studies about that, or any kind of comparison about that?
Yeah, so for explanations, so actually that was my last point of the slide. I didn't go into the detail of that. So this is like explainable AI is a hype right now, let's say. So this has been done, the explanations have been generated using knowledge graphs and recommender systems a lot. So they are like, so it's mostly post hoc explainability. So the recommender system first does its recommendation, and then they try to generate paths from these recommendations to explain why this recommender system recommended the things that it did. So there are studies on that, yes. There is one book by Ilaria Tidi, Freddie Lissu, and Pascal Hitzler. So they are working a lot on that. And there is, in this book, there is one chapter which is actually listing these approaches. So yeah.
Thank you. I actually misunderstood the point about the explainable AI when you made it. I thought it's explaining how the graphs are built, not that the graphs are built for explaining. Okay, now I get it. Yes, thank you very much. And to my last question. So I had a couple of questions which have to do with how practical results, how close to the human ones. And what I still think is that, yes, there is still a lot of work, especially when we're talking about creating an initial ontology or knowledge graph that, well, involves other experts, or maybe some people who will take something generated by the automatic methods and then do some work with it. But anyways, do you think that within like next 5 years or 10 years, we will have the process fully automated? I mean, for example, let's talk about texts and everything there. Text had pretty good results before attention, before BERT and everything, but then weren't really practically usable. They were interesting, but when you showed them to a real person who had nothing to do with AI, he wasn't impressed. Situation changed when we had when attention came, but more importantly, I think, when we were able to create methods which can actually consume terabytes of information. So by being able to feed something to a network which doesn't need any kind of teacher other than the text that's given, we were able to create state-of-the-art networks that are actually useful, and when you show them to people, they can't really distinguish fake news from real news, for example. Do you think that this is possible for everything that has to do with knowledge graph? And if you think so, when will it happen, and what kind of breakthrough are we waiting for?
Yeah, so this is a very good question. It's like using these knowledge graphs for example, other things like fact checking and these kind of information, right? So actually there are studies now on that also. So it is, how can I say, it is starting to happen a lot in the past few years. So they are checking again, they are using these knowledge graphs as the background to check on the facts. So this is what in some of them, I mean, I'm just saying it naively here, but there are some studies which have started happening. So they are doing this misinformation detection and these kind of things with the knowledge graphs, but it is a beginning, I think, right now. So this has begun to happen. There is, I think, there is the lab of Rafael Fonsi. They are working on misinformation detection. Also, there are some people in UK and KMI, they are doing the similar things with knowledge graphs. Yeah, but I don't know too much into the detail of that, but I have seen this passing by my, vision in the conferences, yes. Yeah.
Yes. Yeah, but what do you think about some kind of technology, breakthrough, whatever, that will be able to just take a corpus of texts, like I said, several tens of thousands of texts, and give us a knowledge graph specifically tailored for our tasks that is as good as if it was done by an expert. Is it even possible? And what kind of time are we talking about?
This is so. These things are happening for a long time, but they are not accurate. I agree with you on this. So this is so for example, as I said during the presentation, that DPpedia was generated from Wikipedia, and we still, so I didn't talk about that study. We still have this information which is missing from there, or it is wrong. A duck is assigned a type person. So these are the kind of informations that we are getting out of this. The point is then what they are doing now is, so what we have done, that we have tried to correct this information after it has been generated automatically. Of course, this is also not as close to human as possible. No, not yet. I don't think it is really close in time that we will get that close to human. But I think, in my opinion, I think that human intervention at some point is necessary. You cannot just automate, So this is what is, how can I say, this is this field of study about human in the loop for this kind of things, So
okay.
Yeah, I see your point, yes. Mm-hmm.
Thank you very much. Yeah. Was very interesting.
Thank you.
Konstantin, those were all my questions. Thank you.
Thank you very much. Interesting questions, by the way.
Okay, I should ask about any other questions, but really we speak about 2 hours. It's yeah, only half of our listener stay in YouTube and here, and I suppose it's too difficult for people listen so long. Okay, any other questions in any chats, YouTube and other? And if no other questions, we will finish.
Just to say one thing, in case if you have any questions, I will leave my email in the chat also. So you can just contact me. I will do that now. I should have put it on the slide, but here it is. Yeah.
Okay, could you share your screen with email for people which...
I shared it in the chat. Okay, sorry.
Yeah, because chat is unavailable for YouTube.
Yeah, exactly. I just realized that. Just a second. For the moment, I actually forgot. So I will just type it here. So yeah, so you can just contact me here if you have any questions, and if you want to know more details about something, yeah, just send me an email.
Okay, thank you very much. We will finish with this then. I'm happy very much that you come to us and present these results and perform review of this big topic of studies. And it's really very good, very interesting topics. And maybe Alexei want to say some last words.
Yeah, so thank you very much, Mehvesh. I'm very happy to hear you at this location.
Yeah, definitely.
Yeah, so if someone else wants to present something to us, we would be also very happy.
Yeah. Okay, then I would just thank both the hosts and all the audience for very interesting questions. It was a very nice discussion. Yeah, a few parts I went a little bit faster just to compensate with the time, because it was feeling like it's going on longer and longer. So yeah, I hope you enjoyed everything.
Yeah, thank you very much.
Thank you very much. Okay, I'm finished. Have a nice day. Goodbye to all.
Bye-bye.
Goodbye.